Great. Thank you very much, Gary. And good morning, good afternoon to everyone. And thank you for getting up at some very early times of the morning for some of you to join this session today. This presentation is one that I recently gave last month at the North American Water Loss Conference in Texas. And it's building on some of the presentations that myself and Alan Lambert have done over the last couple of years onto the causes of low ILIs in small systems. This particular presentation is not really focused on the theory because we've already had many sessions on that, but is looking at some of the results that we're seeing from customers in different parts of the world who've been using system correction factors to tailor their UARL calculations. So the first thing we're going to do is to look at the relationship between the UARL, the ILI, and system correction factors. We'll talk a little bit about the free water audit software version 6 and their concept of a boundary case. And we'll also have a quick recap on what a system correction factor is in case it's something you're not familiar with. We'll then look at some theoretical scenarios where you may be using system correction factors. The first scenario is where you're calculating a whole system ILI. The second is where we have certain characteristics of a system or a zone or a DMA, where a standard 1999 UARL calculation would tend to over-predict UARL volume. And then we'll look at boundary cases where a standard UARL equation tends to under-predict UARL volume. And this will give you an idea of the kind of system characteristics where you're going to get that over or under prediction, and therefore where it may be useful to have a system correction factor calculation. And then we're going to look at 3 recent large case studies. The first is for Water Services Corporation in Malta. The second is for the whole of Quebec province in Canada. And the third one is for Sydney Water in Australia. So we'll kick off by just looking at some of the relationships between UARL, ILI, and system correction factors. In the free water audit software version 6 from the AWWA, it talks about the use of system correction factors and the fact that the free water audit software will calculate a UARL and ILI for any size of system at any pressure. But it does bring into play this idea of boundary cases. So a boundary case is where you have certain characteristics, where you have small systems, lower or very high average zone pressures. And in these scenarios, you may get over or underestimation of UARL volumes. And that's because they're operating at or near the limits of the original model assumptions made in the 1999 equation. And there's a reference at the bottom, which is referenced in the free water audit software acknowledgements to the Leak Suite Library reference paper on this. So what is a boundary case? A boundary case is where you have a whole system, or it could be a zone within a system or a DMA, where you've got less than 5,000 service connections. You've also got average zone pressure, which is less than 64 PSI or 45 meters, or it could be greater than 85 PSI, in other words, greater than 60 meters. So if you've got these, if you've got small systems or you're operating at lower pressures or higher pressures, then this is considered to be a boundary case. And this is where you're going to get either an overestimation or an underestimation of UARL volumes. It's important to note that if you don't have these conditions, so if you're operating in a system or a zone or a DMA with more than 5,000 service connections, or your pressure is sitting between 64 PSI on 85 psi or 45 to 60 meters, then the standard 1999 UARL equation will be absolutely fine for you to calculate your UARL volume targets. So a system correction factor is a way by which you can optionally customize the original 1999 UARL equation for any system or zone or DMA. And the formula for it is simple. A UARL with system correction factor volume is the value of the system correction factor, which you get from the SCF software, multiplied by the UARL volume calculated using the 1999 equation. What it does is it takes into consideration the specific characteristics of that system, zone, or DMA. So it will include things like the system size, the density of connections, the average zone pressure, and the specific combination of rigid and flexible pipes on services and mains. So it's suitable for very small utilities or DMAs. Some of the calculations that we've got in the case studies are as small as 5 service connections, but it also can also cope with larger calculations for whole utilities or larger systems or zones. Ideal for many small utilities. There are a large proportion of those in the USA, but also in other parts of the world. The SCF calculation will give you a wide range of information which you can use to get insights into where to target leakage reduction and pressure management opportunities. And it is a separate calculation from either the AWWA free water audit software or from any other software you may be using to calculate a UARL. So it's different. A UARL with SCF calculation is different in a number of ways. It shows the influences which can be combined on UARL volumes, which were not part of the original 1999 UARL equation. The first one of those is FAVAD, fixed and variable area discharges. So this is the influence of pipe materials on the pressure leak flow rate relationship. And the UARL with SCF software uses an N1 of 0.5 for fixed area leaks on rigid pipes and an N1 of 1.5 for variable area leaks on flexible pipes. It also uses an N1 of 1.5 for unavoidable background leakage, which can make up about 60% of UARL leakage. The second influence that it takes into consideration is the influence of small systems on burst frequencies. So in small systems, in any one year, you may not get any UARL bursts. And so what the Poisson distribution does is it models the median or 50% chance of exceedance in any year, the median values for UARL burst frequencies, rather than the average. And this probability distribution is very appropriate for use for small systems because it uses the median values of burst frequencies for small systems, but as the system size gets larger, then the probability distribution changes to model a normal distribution using average UARL burst frequencies. And the third influence that is taken account of in the SCF calculation is the pressure bursts relationship. What the software does is it will show you the individual influences of these three different effects of FAVAD, Poisson, and pressure bursts, but you can also see them cumulatively as well. So what we're going to do next is take a look at some scenarios of when to use a system correction factor and when not to use a system correction factor. And the first scenario is when you are calculating a whole system ILI. So the infrastructure leakage index, this is the ratio of current annual real losses to unavoidable annual real losses, and you can see the equation on screen there. And you should always initially calculate your whole system ILI using the 1999 calculation for UARL. You can use the free water audit software to do this, or other software you may have, which calculates that whole system ILI. Then, if you find that you have less than 5,000 service connections and or your pressure is less than 45 meters or greater than 60 meters, or less than 64 psi or greater than 85 psi, then you could consider an SCF calculation. These are the characteristics for this boundary case. What that SCF calculation will do is it will show you how low your UARL leakage could go for your whole system, or a zone or a DMA within a whole system. And it will show you how much UARL leakage you could save by reducing operating pressure by small amounts. We're going to see some examples of this coming up. So that's the first scenario, which is really important. Calculate an ILI. This is for comparisons between utilities using the standard 1999 equation. The next scenario is looking at the kind of conditions where a standard UARL equation will tend to overestimate UARL leakage. This tends to happen when you've got low average zone pressures, less than 64 psi or 45 meters. You've got a small number of service connections, less than 5,000 service connections, and you've also got high percentages of flexible materials on services and mains. And these conditions can also result in ILIs of less than 1 using the standard UARL equation. So what we're going to do is we're going to work through an example to see what an SCF calculation can tell us. In this example, we've got 3,000 service connections, average length of private service pipe, 5 foot per connection, with a mains length of 50 miles, an average zone pressure of 50 psi. In terms of mains and services, we have 60% rigid mains, 40% rigid services from the mains to the property line, and 30% rigid services from the property line to the meter. When we put that into the system correction factor software, we get the results that you can see in the pink results section here. I'm just going to talk through some of them. We get a value of SCF, which considers the FAVAD effect, the Poisson effect, and the pressure bursts effect of 0.74. Now, to make that meaningful, if you consider that the value of an SCF using the standard UARL equation would be equal to 1, then an SCF equal to 0.74 means that in this particular system with these particular characteristics, the standard UARL equation would overestimate volumes, UARL volumes by 26%. So that's the difference between an SCF of 1, representing the standard UARL volume, and the system correction factor using the FAVAD, Poisson, and pressure bursts influences. If you want to see us in volume terms, if we did a standard UARL calculation for this system, we would get a volume of just over 37,000 US gallons per day. But if we use the system correction factor software, we can see that actually we could go as low as 27,602 US gallons per day. So in this particular system, because it's a small system, it's got less than 5,000 service connections, it's operating at low pressure, it's got a good range of flexible pipe materials on mains and services. We could actually set more aggressive UARL leakage targets and go even lower than the standard UARL equation would suggest. This table and graph also come from the software. The graph on the left-hand side plots UARL volumes in US gallons per day on the y-axis against average pressure in PSI on the x-axis. I don't want to spend too much time on the graph apart from to say that you can see that all of these curves, and I'm particularly interested in the red one, which is the UARL volume with the effects of FAVAD, Poisson, and pressure bursts, rises sharply as pressure increases. But I want to draw your attention to this table on the right-hand side. At 50 psi, the standard UARL 37,090 US gallons per day against an SCF volume of just over 27,600. What you can use this table for, which is really useful, is you can start to look at where, if you can drop pressure by small amounts in certain systems or certain zones, you can use the table in the SCF software to work out what the savings in UARL leakage could be. If you drop the pressure down by 5 psi to 45 psi, then the SCF volume would drop from 27,603 US gallons per day to 23,748 US gallons per day. Now, in this particular zone, you may or may not be able to drop the pressure by 5 psi. Even if you could only drop it by 1 psi from 50 to 49, then the UARL volume could be reduced, in this case, by 771 US gallons per day, or 281,000 US gallons per year. So you can start to see the value of the SCF calculation, particularly using this table, if you're trying to work out where you could actually concentrate most effectively your pressure management activities. The next scenario shows an example where the standard UARL equation tends to underestimate UARL leakage. So we're looking at the other side of it now. This can typically happen in zones, DMAs, or systems where you've got more than 5,000 service connections and you're operating at pressures of higher than 60 meters or 85 psi. You may also have high percentages of flexible pipe materials. So let's look at another calculation. Basically, this is the same example, but we've just doubled the number of service connections from 3,000 to 6,000. We've got the same average length of private service pipe. We've doubled the mains length from 50 miles to 100 miles, and we've doubled the average zone pressure from 50 psi to 100 psi. And we've got exactly the same percentages of rigid mains and services as in the previous example. This time, when we put this example into an SCF calculation, we end up with a system correction factor of 1.19. Consider again that a standard UARL calculation would have an SCF equal to 1. What this means, a system correction factor of 1.19, is that the standard UARL equation is underestimating UARL leakage. And if we want to see that in volume terms, the standard UARL calculation would give us a volume of 148,360 US gallons per day against a UARL with an SCF calculation including the FAVAD, Poisson and pressure bursts influences of 177,218 US gallons per day. So if we've used the standard equation here to set our UARL leakage targets for this system, what this is telling us is we're very unlikely to be able to meet them, okay? Because the SCF calculation is telling us that the lowest we can go is 177,000 US gallons per day against the standard calculation of 148,000. If we take a look at the graph and the table again, on the graph on the left-hand side, we've got UARL volumes in US gallons per day. And on the x-axis, we've got average pressure in PSI. Again, you can see the general relationship between pressure and UARL volumes. And again, I'm showing you this table on the right-hand side. So the first thing to note, as I just mentioned on the previous slide, is that for this particular system, any UARL targets set using the original 1999 UARL equation are unlikely to be achievable unless you do some pressure management in this zone or system. If we take the pressure down to 95 psi, we can use the table and it will suggest we could actually set our targets as low as 161,107 US gallons per day. Again, it may or may not be possible to drop the pressure by a whole 5 psi, but we can use the difference, a fifth of this difference, to predict that if we just reduce average zone pressure by 1 psi from 100 to 99, we would reduce our UARL volume by 3,222 US gallons per day, which is just over 1.1 million US gallons per year. So think of a UARL with SCF calculation not only as being useful for your smaller systems operating at lower pressures, but you can see here in larger systems operating at higher pressures, you can see that, you know, exactly how you can use this software to show how much you could save in UARL leakage just by dropping pressures by small amounts. Okay, I'm going to move on now to the case study section. So these are some of the case studies where we've got customers in Europe, Canada, and Australia who've used the UARL SCF software to perform calculations in the last 12 to 18 months. The case studies in this section are all very different from one another. We've got one case study which is comprised of many small zones and DMAs. We've actually then got a whole provincial survey in Canada in the province of Quebec, where we have over 600 individual utilities submitting their data for calculation. And then we've got a large state capital utility in Australia. This is particularly interesting because it's got a four-tiered system of organization, starting with pressure zones at the bottom, which roll up into supply zones, which roll up into distribution systems, and finally roll up into 13 delivery systems. All the case studies have got a wide range of size of individual zones, DMAs, or whole systems. They're all operating at very wide ranges of operating pressures. And there's a very diverse mix of rigid and flexible pipes across services and mains. For each case study that I'm going to show you, SCF calculations were not just done for boundary cases. They were actually done for every zone or a DMA within the system, as well as a calculation for the whole utility at the top level. And what's been very clear in working with the customers and doing these calculations with them is that doing SCF calculations across the board gives a great top to bottom or bottom to top picture of that utility or the province, allowing the utility to actually drill down to look at the characteristics and the calculations for each individual zone or DMA or roll-ups of those individual zones or DMAs. This allows the utility to target set at different levels of the water network and helps with decision-making about where it's going to be most effective to concentrate active leakage control and pressure management activities. All of these case studies were performed in metric units, but the software works in either metric units or US units. So the first case study is for Water Services Corporation in Malta, which comprises two Mediterranean islands of Malta and Gozo, with roof storage tanks throughout. Just over half of Malta's potable water comes from 3 reverse osmosis plants, and the remainder comes from underground aquifers. The characteristics of this utility: 130,000 service connections, just over 2,000 kilometers of mains, with an average pressure of 32 meters, with customer meters located at the curb stop. 93% rigid mains, but only 5% rigid services from the mains to the curb stop. In total, 320 UARL with SCF calculations were performed to map all zones and DMAs in 4 regions across the 2 islands. And Water Service Corporation latest ILI is 1.8. A really concerted effort by the team at Water Services Corporation. Their ILI in the year 2000 was approximately 20. So you can see the work that's been done to get that down to 1.8. The case study characteristics. So in terms of system size, nearly every single zone has less than 5,000 service connections. The calculations that we performed ranged in size from 5 service connections up to 14,000 service connections, with managed average zone pressure ranges from 17 to 74 meters. What I'm going to show you now are two scatter graphs. The first one that you can see on the left-hand side, that plots the value of the system correction factor on the y-axis against the number of service connections on a log scale on the x-axis. And so this shows the values of the system correction factor for all the calculations. We've got a value of an SCF of 1, and we've put that line on the graph there just to get you to remember that an SCF equal to 1 is equivalent to a standard 1999 UARL equation. Okay, a UARL with a UARL calculation is not an absolutely 100% precise calculation. So when we're looking at these results of system correction factors, we're really looking for large variances away from that standard value of 1. So anything that sits plus or minus 10% around the standard UARL calculation is going to be just fine. Efficient. But what we can see in this case study is that all the SCFs sit below a value of 0.9, okay, all of them. It doesn't matter the system size, it doesn't matter the pressures in these cases, they're all sitting below 0.9. What that means is that the standard UARL equation from 1999 is overestimating UARL leakage targets. So they could set more aggressive targets here. And we're seeing some SCFs as low as sort of 0.4. I think there's one about 0.39. I think the highest one we've got is about 0.84, 0.85. We can also see the graph of the system correction factor on the y-axis against average zone pressure in meters on the x-axis. There's a beautiful trend you can see here that as the average zone pressure in meters increases, so does the value of the system correction factor. So this is just another way to see exactly the same data. One important thing to point out at this stage is that although we're looking at the number of service connections and how that plots against the system correction factor and the average zone pressure against the system correction factor, the system correction factor is also influenced by the density of connections, for example, and the percentages of rigid and flexible materials on mains and services. What we saw in summary were SCFs which ranged from 0.39 to 0.86 at their range of current operating pressures, which meant that the standard UARL equation was overestimating UARL volumes in some zones by between 61% and 14%. But why are these SCFs all so low? Why were they all below 0.9? Water Services Corporation has had a continuous program of pressure management over the last 20 years or so. And they have a very large percentage, more than 99% of small systems with less than 5,000 service connections. So they're definitely in this boundary case scenario. They've got mostly flexible materials on their service connections. So Water Services Corporation are using these calculation results in conjunction with the snapshot ILI technique. This allows them to very quickly identify zones where lower leakage targets could be set and to be able to better quantify leakage and burst reductions from further pressure management activities. The second case study is for Quebec province in Canada. This case study is actually taking data from 626 individual water utilities within the province, which, if taken together, comprises just over 2.1 million service connections, over 41,000 kilometres of mains, with an average zone pressure of just under 50 metres. Overall, 67% rigid mains and 95% rigid services from the mains to the curb stop and the curb stop to the meter. In total, 855 UARL with SCF calculations were performed to map DMAs and zones across 17 regions of Quebec province. Quebec province overall, their latest published ILI was 6.6 in 2019, but 65% of the individual water utilities achieved a low or moderate ILI of less than 4 in 2019. So overall, in Quebec province, we found that more than 88% of zones were considered small systems with less than 5,000 service connections. And the calculations that we performed went from zones as small as 5 service connections to over 377,000 service connections, with average zone pressure ranges from 18 to 102 meters. So here's the plot system correction factor on the y-axis against the number of service connections on the x-axis on a log scale. Here's our value of 1 representing a standard 1999 UARL equation. We can see here that this particular chart looks very different from the one for Malta, in that we've not only got a large range of values of the system correction factor sitting below 0.9, we've actually got some popping up above 1.1 as well. So for these results in this green dotted box, all the SCFs are below 0.9. We know in these particular zones or DMAs, we could drive our UARL leakage targets further down. The standard UARL equation is overestimating how low we could go. We could get down further. And if we've got any zones or DMAs sitting in this red dotted box, then we know that if we've set targets for those zones based on the standard 1999 UARL equation, we're unlikely to be able to meet those targets without pressure management activities. We can also see here that we've actually got quite a good spread of results sitting between 0.9 and 1.1. This is, if you like, the plus or minus 10% around a standard UARL, which means that a standard UARL calculation for these systems would be just fine. And these tend to be the systems with more than 5,000 service connections on the whole. We can also see the result plotted, the system correction factor on the y-axis against average zone pressure in meters. On the x-axis, again, we see that lovely relationship that as average zone pressure increases, so does the system correction factor. Just another way to see the spread of data for those zones or systems which have an SCF below 0.9 in the green dotted box, and those which have an SCF of above 1.1 sitting in the red box. So we found, in summary, that in Quebec province, we had SCFs ranging from 0.38 to 1.75. What does that mean? It means for some zones or regions, particularly those smaller zones with lower pressures, we were seeing the standard UARL equation overestimating UARL volumes by up to 62%. And for those larger, higher pressure systems, UARL volumes and being underestimated by the standard UARL equation by up to 75%. Lots of reasons why these SCFs are so varied. Some of the reasons for the low values of SCF down to the large percentage of small systems with less than 5,000 service connections, but we have a huge variety of system and zone size, from 5 service connections up to over 370,000 service connections. So that will clearly give a wide spread of values for SCF. Similarly, a wide range of operating pressures, which will also be instrumental in that wide range of values of SCF, and mostly rigid service connections. The SCF calculations are being used as part of the Quebec efficiency strategy, so that the team have a better understanding of their systems and the most efficient way to reach their water loss objectives. The final case study is for Sydney Water in Australia, which supplies over 1.5 billion litres of drinking water to over 5 million people every day. You've got 11 major dams supplying water through 13 water delivery systems. 1.37 million service connections with 20,800 kilometres of mains, with an average pressure of just under 53 metres or 75 psi. 82% rigid mains and 85% rigid services from the mains to the property line. 655 UARL with SCF calculations were performed, and this mapped all pressure zones rolling up into supply zones, a number of distribution systems, and then up into 13 water delivery systems. Latest published ILI for Sydney Water is equal to 1.3. So the case study characteristics. We've still got a large proportion of small systems in this case study, more than 68% of zones. And in terms of the calculations that we performed, some of the calculations were for zones as small as 12 service connections, and some of the roll-up calculations for supply zones and distribution systems and delivery systems were as large as over 384,000 service connections. And we've got, again, a wide range of average zone pressure from 15 metres to 137 metres. Okay, again, the plot of the system correction factor on the y-axis against the number of service connections on a log scale on the x-axis. We have our value of an SCF of 1, representing the standard 1999 UARL calculation. Again, a bit like the calculations for Quebec, we can see a good spread of results sitting under the 0.9, and we've got a few more popping up above an SCF of 1.2. And we've also got a good spread of results which sit in that plus or minus 10% around a value of 1, indicating that the standard UARL equation is fine for setting targets in these zones. So any of the results sitting in the green dotted box, we know that the standard UARL is overestimating UARL volumes. We could drive those leakage targets further down. And for the zones and systems and DMAs sitting in the red box, we know that the standard UARL is underestimating UARL leakage. And if we're going to try to hit that target, then we're going to have to do something about the pressure in those systems to bring that value down. And again, if we look at the results as the system correction factor on the y-axis against average zone pressure in meters on the x-axis, again, we see the relationship that the system correction factor increases as pressure increases. And we can see, again, the spread of results sitting in the green box with an SCF of 0.9 and below, or in the red box with an SCF of 1.1 or higher. So what we saw in Sydney Water were SCFs at current operating pressures ranging from 0.37 to 1.95. So for some zones, typically the smaller zones with lower pressures, standard UARL equation was overestimating UARL volumes by up to 63%. And for some other zones, typically the larger, higher pressure zones, we were finding that the standard UARL equation was underestimating UARL volumes by up to 95%. And again, the reason that these SCFs are so varied is we've got a very wide range of operating pressures and a very wide range of system and zone size, mostly rigid mains and services. Sydney Water are using these calculations to contribute to their complete assessment of all their pressure zones, supply zones, distribution zones, and delivery systems. And this is going to help them with better targeting of active leakage control activities and pressure management activities. So in summary, there is no practical lower or upper size limit for a UARL with SCF calculation. We're seeing calculations within practical pressure ranges of 10 to 200 PSI. Great for small utilities, also very suitable for calculations, as we've seen, for large utilities such as Sydney Water, and for statewide surveys such as the one you saw for Quebec province. Remember to calculate a whole system UARL and your ILI using the standard 1999 UARL equation, and consider using SCF calculations for boundary cases. Those are systems or zones or DMAs with less than 5,000 service connections, which may also be operating at lower than 45 lower than 45 meters pressure, or higher than 60 meters pressure. Or what you could do is use SCF in the way that these case studies have shown, so that you can get a map of all the zones and systems within your utility, and then have that complete top-down, bottom-up view. If you do this, then you'll be able to look across your utility and identify which zones and DMAs can have their UARL volume targets reduced, which zones and DMAs may not be able to achieve UARL volume targets which had been set using the standard 1999 UARL equation, and target zones or systems where further pressure management may be possible, and to be able to see from the tables within the SCF calculation what those volume reductions would be. If you think back to earlier in the presentation where we were looking at some scenarios where you can see if you drop the pressure by, say, 5 PSI, or might be 5 meters, how much volume reduction you could quantify from that activity. And these case studies have shown that even in utilities with low ILIs, like Sydney Water, like Malta, and even when you do calculations and see that some of the DMAs and zones have got low SCFs, further UARL volume reduction is possible, even with low SCFs and low ILIs. One of the things that we've been working on over the back end of 2021 is to use SCF to calculate a power law. That's just something to tease you with. We might have some more news on that later in the year, but it's going to be new functionality coming to the software at some point later on this year. So that's the end of my presentation. Thank you very much for your attention and for taking the time to attend today. I hope you found the case studies useful in seeing the power and potential of SCF calculations. Alan and I are now both available if anybody has any particular questions they would like to ask. Thank you.
Thank you very much, Kate. That was very informative. If anybody does have any questions for Kate or Alan, then they can type them into the chat function, and I'll ask the questions to them. One thing that I wanted to ask Kate while people type their questions in is, on one of your slides you mentioned about the software being online, the SCF software being online. Where can people access that?
So the software is available from the WLRNA website, and I'll type that in the chat box.
Okay.
Yeah, it is a paper calculation option. So if you want to do one, you can just pay for one calculation. If you want to do 500, you can pay for 500 and there are volume discounts.
Right, okay.
And if anybody's got any questions about that or wants further demonstrations, then I'll also put my email in the chat box as well.
Okay. We've got a question from Zolt, which is from Budapest. Is this presentation available for download? I assume people can email you directly and ask about the presentation?
Yes, I can give PDFs of the presentation. Also on the website, which is in the chat box, there is a recording of the presentation done just after NAWL with an audio track on as well. So, and of course, this presentation will be on YouTube as well for the water loss specialist group.
Yeah, so we're recording this and it will be uploaded to our YouTube channel. So hopefully everybody knows where the YouTube channel is. One, I noticed at the beginning you were talking about the pressures and saying that the SCF is better for pressures. Was it below 64 psi and above 85? Yeah.
So what we're seeing is that if your pressures are between those ranges, so I'll talk in meters because I know the presentation was for the American audience initially, but 45 meters to 60 meters, if your pressure is sitting within there, then you'll tend to find that a standard 1999 calculation will be fine. It's when the boundary cases are when you get pressures lower than 45 meters and pressures higher than 60 meters. And you've also got small numbers of service connections.
Yeah, that's quite a narrow band though, isn't it? Between 45 and 60. I would have thought most utilities are operating below that or above that, and not so much would be in that range.
We actually see, I mean, some of the case studies that that we've looked at, there's a good proportion. They're the ones that are sort of sitting in that band of, an SCF of 0.9 to 1.1. They tend to be the systems or individual zones or DMAs, which are operating, just around that sort of 50 meters, 55 meters pressure.
Yeah. Okay.
Yeah. But then if you've got a company like Water Services Corporation in Malta, they're always trying to drop their pressure, just shave little bits off their pressure. So they've actually then got an awful lot of systems and DMAs and zones operating at less than 45 meters, which is one of the reasons why their SCFs are all below 0.9.
Yeah, okay. So we've got a question from Brian, which is, do you find the same zones above and below the SCF of 1 in the plots using connection and pressure, or do you find different results using the different parameters?
No, it's just exactly the same zones. It's just a different way of looking at the data. Yeah, it's exactly the same zones.
And I did notice if you looked at the graphs, you could see like the very highest one, it was obviously the same zone.
Yes, exactly.
Which had the same SCF, but it was just moving across depending on whether it was with connections or pressure.
Yeah.
And will there be when you say there's something new coming up, will that be in time for Prague, or will you be presenting something new in Prague or not?
I hope that we'll have something to add to the presentation in Prague. We'll have some new case studies, some further European case studies to share, hopefully in Prague, as well as some data, hopefully from South Africa. I'll be working to get some more information on the power law concept. I'm sort of dragging Alan a little bit out of retirement occasionally, just to add some new functionality. So,
nobody really believed he was retiring.
Well, actually, he has.
Fully retiring, sorry, fully retired.
Fully retired. obviously it's an excellent opportunity if anybody's got a question for Alan, because he's not often on these calls and available for questions.
Yeah, that's true. If anybody has a question for Alan, I suppose it doesn't have to be on the SCF.
No, I'm sure he'll talk about anything.
Okay, so we've got a question from Ryan. How about systems that have less than 10 meters pressure? What will be the right range assumptions of SCF? And I mean, this is quite common in Asia or Southeast Asia, should I say? Ryan's from the Philippines, but it's quite common in a lot of Southeast Asian countries like Indonesia, Thailand, even Malaysia in some places.
Mm-hmm. I'm trying to think about the lowest values. We've done calculations for very low systems, low pressure systems, haven't we, Alan? Some of the...
Yes, I think that when you get down that low, I've always been very careful from first developing the UARL 20 odd years ago, not to extend the assumptions beyond the data that we have, or the ones that we can check that it actually works before going public with it. And that's why we tend to put these lower limits on. We're getting good comparisons with URL with SCF, working down to about 20 meters with advanced systems, high-income countries with very good data. And we're seeing that it can work well in those systems. But we haven't got any situations yet of much lower pressures with very, very good systems to work with. So at this moment, I'd be very cautious about that. But I also work with Professor Cobus van Zyl, who's at Auckland University now. We've been working together on this with the theory for many years now. And some interesting things start to happen when you get down at those very low pressures of 5 to 10 meters. So I think that is something where further research will need to be done, probably not by me, but by other people, but using the same kind of principles of looking at the pressures, looking at the pipe materials, looking at the system size, and that what we've got here might be the forerunner of extending to even lower pressures and even higher pressures than we've validated at the moment.
I would just say to Ryan, if you want to get in touch with me, Ryan, I'm happy to run through a couple of sort of test calculations with you if you're happy to send me some data to work with to see what happens when we get to less than 10 meters pressure. So just email me and we can work through a few calculations with you. Okay.
That's great. There doesn't seem to be any more questions. Everybody seems to be a bit quiet today, which is strange. Maybe they're all camera shy. But, okay, well, thank you very much, Kate and Alan as well. And this was just a one-off webinar, everybody. So this is not the beginning of the series, but hopefully we'll see a lot of you in Prague in person. And of course, there'll be lots of presentations on probably SCF and, as Kate said, new case studies. So, and other water loss subjects as well. So hopefully we'll see a lot of you in Prague in June. But for now, thank you very much, Kate, Alan, and we'll see everybody again soon.
Thank you.